Final talk is by Ned Batchelder, Pragmatic Unicode, or How to Stop the Pain.
Hello. Yeah. Hi, everyone. My name is Ned Batchelder. I've been working with Python for well over 10 years. I'm going to talk pretty fast during this talk, partly because I have a lot to say and partly because I grew up in New York City. I've been working with Python for about 10 years, which means at least a dozen times I've made all the same mistakes supporting Unicode that you probably have, that have caused you pain, that have brought you to this room to try and find a way to stop the pain. So let's talk about how that happened. What happened in the past was you wrote a program and you were really happy because it worked. You had this great program. And then all of a sudden something weird happened. A strange character appeared in your program and errors happened and you were sad. Okay? That is the past. That's not going to happen anymore. 25 minutes from now you will know everything you need to know to not have that happen. But the way you're feeling right now is you're annoyed, you're angry, and you're fundamentally uninterested in Unicode, right? So I'm going to try to keep this really straightforward and just tell you what you need to know. I'm not going to get into all sorts of weird esoterica, okay? By the way, there are no images in this talk. There's a lot of Python making this happen, yeah. I'd be glad to show anyone afterwards all the craziness I did to make this talk. But what's going to be in this talk? There are going to be 5 unavoidable facts of life that you have to accept, and there will be 3 pro tips that will tell you what to do about them. And once you keep those 8 things in mind, Unicode will never again be a problem for you. That's my promise. It's a big promise, but I think I can make it work. So first, let's talk about the world and Unicode. The first fact of life is that computers deal with bytes. There is no such thing as sending Unicode to someone. There's only sending bytes to someone. You don't send them text, you send them bytes. You don't store text, you store bytes. Everything is bytes. That's just the way the world of computing works. To send people text, what we decided is, because bytes are meaningless, that we would assign meaning to bytes through convention. And the most basic convention for text is that there's the ASCII code, where we've taken 95 graphic symbols and assigned them byte values and said, when I send you this byte value, you will know that I mean a capital letter A, because we've agreed that these bytes mean this. ISO 8859-1, also known as ISO Latin 1, added 96 more characters for bytes, and then Windows added 27 more characters, and this is sort of the extent of what you can do with bytes for text. Okay, that's about as many different symbols as you can display with a single byte. Fact of life number 2, 256 symbols is not enough for the world to communicate text. There's a lot of languages out there. They all have their own writing systems. They all demand a seat at the table. No one's going to say, you have to speak English, right? So back when your program was broken and you were dropping in encodes and decodes at random to try to make the problem go away, yeah, right? I'm looking at you and you and you. Yeah. I'm sure there were times where you were gritting your teeth and thinking, why can't they just speak English, right? It doesn't work that way. You cannot change the world. You have to change your program, okay? So all of that encode and decode whack-a-mole that you used to do to make your programs work, you don't have to do that anymore, but you do have to accept these facts of life. So to deal with the more than 256 symbols needed, the first idea was, why don't we just have a bunch of different 1-byte character codes, right? So we'll map single bytes to characters like ASCII and ISO Latin 1 do, but we'll pretend that fact of life number 2 doesn't exist by just having lots of different codes. And that just added to the confusion because there are all these different codes, and it meant that at any one time we could only still use 256 symbols at once. And there are single languages out there that have more than 256 symbols, not to mention that we need to mix them together, and there's special symbols, and there's math, and there's snowmen, and all sorts of things that for some reason we need to communicate. So single byte character codes don't work. So the next great idea was, well, why don't we just use 2 bytes? And what we'll do is, we're not clicking anymore, excuse me. So we'll use 2 bytes. But that didn't help either because, as it turns out, even 65,000 symbols isn't enough, and there were multiple different 2-byte codes, and people couldn't agree on them, and there were various problems with them. So what we finally come to is this thing called Unicode. Unicode fundamentally is a giant catalog of characters assigned to integers. And the structure of the code means that there are 1.1 million possible characters. And as of now, only 10% of them have actually been assigned. So there are 110,000 characters in Unicode. We've used up 10% of the space. We've already covered all of the really big languages in the world, so it looks like we're not going to run out of space. So this might be the last character code we need, which is good news.
Until we meet the aliens.
Until we meet the aliens, right. Okay. Huh? Klingon is not in Unicode. I can explain why later. One of the great things about doing talks at PyCon, by the way, if you don't know, is that you take a topic that you think you know everything about, and you promise to tell people about it, and along the way of writing slides, you discover all the things you didn't know about it, and now you know much more about it. But Unicode has all sorts of things. It has the textual symbols that we're used to. It has the funny symbols like the snowmen. It's got all of the writing symbols in the world, and it's constantly being upgraded. We're up to Unicode 6.1 now, and one of the latest characters to be added to Unicode is pile of poo. Which I guess is important to someone. Here's a sample of some exotic Unicode characters. Every Unicode character, as I said, is assigned to an integer. That integer is called its code point. It's written with a capital U, a plus, and then hex digits. So for instance, the double-struck capital P is Unicode 2119. Every character also has an unambiguous uppercase ASCII name. So these names are defined by the standard. And there are ways, for instance, in Python that you can use Unicode characters by their name rather than by their number. This string of characters that spells out Python, I got from going to a site that's designed for teenagers to impress their friends on Facebook by inputting regular English text and picking out Unicode symbols that look kind of like the characters and give you what they call fancy text, which, as we'll get to, is funny but also extremely useful. We're going to be using these 6 characters and examples throughout the talk. But we still have a problem. Remember, fact of life number 1 is that computers only deal with bytes. Right? We've got this Unicode thing, which has 1.1 million integers. Do the math, those won't fit in a byte. We've got to figure out a way to communicate those code points in bytes. And the way Unicode does that is it defines a handful of encodings. And encodings are schemes by which you can take code points and represent them as bytes in a bidirectional fashion so that you can convert them into bytes, transmit them, and then convert them back into code points at the end. There are a number of different encodings. The main one you need to know about is UTF-8. UTF-8 is the king of the encodings. And 2 things that are very important to understand about UTF-8 is that 1, it's variable length. Different Unicode code points will need different numbers of bytes. And the other thing is that all of the ASCII characters are 1 byte in Unicode and have their same values. So ASCII strings are valid UTF-8 strings, which is a very nice property. At the bottom here, you've got the bytes of UTF-8 and the characters they map onto. And you can see that the H and the I, which are ASCII, are 1 byte each. The double-struck capital P, because it's high up in the Unicode code points, needs 3 UTF-8 bytes. It turns out that no Unicode code point needs more than 4 UTF-8 bytes. Okay, that's the fundamentals of Unicode. There's a lot of esoteric stuff that I'm not going into because I know you don't care. So let's talk about Python 2. We're going to cover Python 2 and Python 3, and they're radically different, as you'll see. In the code examples, you'll see that there is a big 2 for the Python 2 code, and there'll be a big 3 for the Python 3 code. In Python 2, there are 2 distinct string data types. One for storing bytes, which is called str, and one for storing Unicode code points, called Unicode. And so, for example, if I define a string with just regular old double quotes, I get a str in Python 2. And if I look at its type, it says it's a str. That is storing bytes. If I create a Unicode literal with a U prefix, then I get a Unicode string. And it is storing code points. okay? Remember, there's bytes and there's code points, and a big theme of this is you have to know what you're dealing with and you have to keep them straight. So there's going to be two data types in Python 2 for dealing with it. To convert between the two, Unicode strings have an encode method, which turns code points into bytes. And byte strings have a decode method that turns bytes into code points. They take an argument, which is the encoding that you want to use for doing the conversion. Okay, so if we take a Unicode string, and this is the high Python string with the umbrella and the double struct capital P, notice that I can insert Unicode code points by using a \u and then 4 hex digits. If you need more than 4 hex digits, you need to go with a capital U and then 8 hex digits. The length of my Unicode string is 9, meaning there are 9 code points in it. If I encode that Unicode string into UTF-8, I get a new variable, a new value, which is a byte string, which has a length of 19, because it's got 19 bytes. I can then take that, when I look at it, I see all the bytes, and they're represented with the \x, which is the byte hexadecimal escape. I can then decode that back from UTF-8 into Unicode and get my Unicode string back. Okay? This is fundamental. Back when you were playing whack-a-mole and just throwing in Unicodes, encodes, and decodes, what you were doing was you were converting Unicode's code points into bytes and back again. But you were probably doing it wrong. So you just need to keep it straight and do it right. The problem with encode and decode, and we're getting to the pain here, the problem with encode and decode is that they might fail. Because not every encoding can deal with the conversion you're asking it to do. So for instance, if we take our Unicode string and try to encode it to ASCII, it's going to fail. And the reason it fails is because the ASCII codec is the coder-decoder that does the work of the encoding, the ASCII codec can't encode the characters at positions 3 through 8 because the ordinal is not in the range 0 to 127. ASCII only goes from 0 to 127. If you try to encode any code point outside that range, you will get this failure. You can even get errors decoding. If I take my UTF-8 string and try to decode it as ASCII, I will also get an error because UTF-8 has values outside the range of 127. And if I take random byte garbage and try to decode it as UTF-8, I will also get errors. There are invalid sequences in UTF-8, which, by the way, is one of its valuable properties. You can tell that you're misdecoding things as UTF-8 because not every sequence of bytes is valid UTF-8. It turns out that there's a second optional argument to encode and decode, which is, what should I do if I can't complete the encoding? The default value for that is strict, which means raise an error, which is why we were getting errors before. But you can also, for instance, say, encode my Unicode to ASCII, and if you get a character you can't deal with, just replace it with a question mark. And we get back the string hi, 6 question marks. We can also say, if you can't deal with it, then insert the XML character reference that represents that character instead. So here I get an H and an I and a space, which are valid ASCII, and then the rest of the things come out as XML or HTML character references, which is very handy if you happen to be producing XML or HTML coming out. You can even say, just ignore it, just skip over that character, and we just get the string hi space. When you're decoding, you can also do the same things. The thing to note is that when you're decoding to a Unicode, instead of an ASCII question mark going in, you get the Unicode replacement character, which looks like these question mark lozenges, but you get lots of them because you got one for every byte in the UTF-8 that you couldn't represent. Python 2 tries to do something very helpful for you. It will implicitly convert byte strings to Unicode strings if it needs to. So for instance, if you try to add a Unicode string and a byte string together, you will get a Unicode string out as a result. And the way it does that is it takes your world string and it decodes it as ASCII to get you a Unicode string, and then it adds the 2 Unicode strings together. This is a lot like how ints automatically get promoted up to floats in order to do float and float arithmetic. Right? So here it implicitly converted world to Unicode, and here I'm showing you the explicit steps that it did behind the scenes for you. And the reason it used ASCII is because there's a thing called sys.getDefaultEncoding, which is ASCII. I can't take a question, unfortunately. You can also get errors when you're decoding. So if I try to add a Unicode string to my UTF-8 string, it will implicitly try to decode UTF-8 as ASCII, and it'll get the same error that we saw when we explicitly decoded it as ASCII. This is why you are feeling pain. Your program will work fine if you ignore the distinctions between bytes and Unicode as long as all of your data is ASCII, because Python 2 will helpfully change all of your bytes up to Unicode with an ASCII decoding, which will succeed as long as the data is ASCII. And as soon as the data is not ASCII, it will throw an exception. And those exceptions are the exceptions you've been seeing. So this is the Python 2 style of pain, right? It tries to make things very easy for your ASCII data, and as soon as your data gets outside that range, it blows up. There's a lot of places these implicit codings errors can happen. Let's just take a look at a few. Here's a byte string format string formatted against a Unicode data string. It has to convert the format string into Unicode and then do a Unicode format, right, to produce a Unicode result. Similarly, you can have a Unicode format string with a byte string. It'll have to decode the byte string to make it a Unicode to do the Unicode formatting to produce a Unicode format string result. If you print a Unicode string, it could fail because it's trying to encode your Unicode string into the output encoding that the print standard out is attached to. So you could get an ASCII codec error when you try to print your Unicode. Lastly, this is the really odd one, and this is why it felt so random that you could just play whack-a-mole with decode and encode. Remember, encode is an operation on Unicode strings, and I'm doing it now on a byte string. I am encoding to UTF-8 and getting the error that I couldn't decode to ASCII. So I asked for two things, and it complained about two other things that I wasn't even talking about. And the reason it's doing that is that encode is an operation on Unicode strings, and I gave it a byte string. And it said, well, I know how to make that byte string into a Unicode string. I'll just decode it as ASCII first to get the Unicode string so that I can do the encoding that he's asking me for. And it's that implicit decoding of the UTF-8 via ASCII that you're getting the error there. I don't know why I have that there. So, fact of life number 3. You have both bytes and Unicode, and you need to keep them straight. This needs to be in your mind. There are two things, and I will deal with both of them. You cannot cover your eyes and hide your head in the sand and just pretend the problem doesn't exist. You have to deal with it. All right, let's talk about Python 3. Of all the changes in Python 3, the biggest change and the reason things take long to port to Python 3 is because of Bytes and Unicode. The characterization of the pain in Unicode in Python 3 is also very different. So in Python 3, there are still two data types, two string types, one for bytes and one for Unicode. If you use a plain string literal in Python 3, you get what's still called class stir, but now it stores code points. And this is a bit confusing. Stir in Python 2 is a byte string, stir in Python 3 is a Unicode string. If you want a byte string, you use a B prefix, and then you get a value of type bytes. I think these names make a lot more sense, and once I understood this, even when I was working in Python 2 code, I would think in these terms and then backport to Python 2, because this makes more sense. There's no coercion. Python 3 will never automatically, implicitly, silently behind your back change your bytes into Unicode or vice versa. If I say, add my Unicode string and my byte string, it'll say, it's a type error, you can't do that. If I ask if these two are equal, Python 2 would have said these were the same, and Python 3 says they're false. It's not equal. If I make a dictionary with a byte string of a Unicode string key and look it up with a byte string value, it will say it can't be found. Python 2 would have given you back the string world there. So the Python 3 pain is you have to deal with this explicitly everywhere. Your program that worked fine with ASCII and then failed with the accented characters doesn't even work with ASCII on Python 3. Okay? This is so central to Python 3 that Python 3 is named after Facts of Life 3. Remember, Fact of Life 3 was you have to deal with both. Python 3 is you have to deal with both. Okay? So the Python 3 pain is much more immediate, which has been a bit controversial. But at least it means that if your code works at the beginning, it'll work no matter what Unicode data it encounters. One more twist on Python 3 is that the data you get from files depends on how you opened it. In Python 2, there's a binary mode and a text mode for opening files, but except on Windows, it doesn't do anything different. On Windows, it fiddles with the line endings to change carriage return line feed into just line feeds. On Python 3, what data you get back from a read operation depends on how you open the file. So if you open it with the default of a text mode, you will get back a Unicode string. If you open it in binary mode, you will get back a byte string. If you read UTF-8 here, what we're getting back here is the wrong string. And that's because the bytes, remember fact of life 1, files only have bytes in them. For this operation to give you a Unicode string, it had to decode the bytes that it saw. And that means it has to have an encoding to use to do the decoding. In this case, there's a thing called locale.getPreferredEncoding, which on the machine I did these slides on is Windows, so it's code page 1252, which means that this UTF-8 was misinterpreted. This is not the right Unicode string to have gotten out the back. So this operation acted just like this operation. If I instead say, I know what's in that file, it's UTF-8, by supplying the optional encoding argument to open, then I get back the string that I wanted. And notice that if I read that as bytes, I just literally get the bytes. By the way, one twist is that standard in and standard out are pre-opened files for you. And so the encoding that they are using depends on how your program is running and where it's running, which can be very complicated. Okay, so let's talk about pain relief. What should you do? Pro tip number 1, your program should use Unicode on the inside. What you want to do is you want to build a Unicode sandwich. You want to have bytes on the outside and Unicode on the inside. And you want to do all of your decoding from bytes to Unicode as soon as possible as data is coming into your program. And then on the way out, you want to encode your Unicode to bytes as late as possible and keep all Unicode in the middle. Keep in mind that you might be using a library or a framework that's doing some of that for you. So for instance, when you get data back from Django or from the JSON module, it's already in Unicode form because it's done the decoding for you. Which brings me to pro tip number 2. You have to know what you're dealing with. The word string is ambiguous. You can't simply say it is a string. It's either a byte string or it's a Unicode string, and you need to know which you have. Ideally, you would do that by design. You would be able to look at a piece of code and say, this is a Unicode string because of its place in the system. If you can't do that and you need to do some reverse engineering, look at the type of the thing. By the way, if it's a byte string, you need to know what encoding it is. Fact of life number 4 is that you cannot tell from looking at a stream of bytes what encoding it is. You have to know some other way. Someone could have told you, right? Joe in the next cubicle could say, I'm sending you a UTF-8 string. The spec could tell you. Lots of protocols have ways of specifying the encoding. This is an HTTP header, this is an HTML meta tag, this is an XML declaration, and this is a coding declaration from the top of a Python file. There's lots of different ways that protocols give you to specify the encoding in the protocol. But simply looking at a stream of bytes without knowing anything about it, you can't tell what encoding it is. Here's an example of our byte stream for our fancy characters, properly decoded with UTF-8, and then improperly decoded as ISO-Latin 1 and UTF-16, and another form of UTF-16, and an old 2-byte shift JIS. All of those decodings work, but they produce garbage. You may be familiar with this style of garbage where there's lots of A hats and A accents. That is the classic telltale sign that you got UTF-8, but you thought you were dealing with ISO-Latin 1. Fact of life 5 that goes along with fact of life 4 is that guy who's telling you what data how your data is encoded, sometimes he's wrong. And you find yourself writing, I'll try it as UTF-8. That failed. I'll try it as ISO-Latin 1. That worked? Okay, maybe. I'm sorry. I don't know what you can do about that. That part just sucks. Pro tip number 3. The pro tip number 3 should just say test. But since this is a Unicode talk, I'll say test your Unicode. And this is where those fancy text generators come in handy. Find yourself one of those Facebook text generators, put in some text that you can read, but is still exotic text, and put it into your test system. It's a great way of making sure that everything works with all of the exotic Unicode characters. Upside-down text is awesome. Fact of life 5.5 is that, the reason it's a half is that you probably won't have to deal with this, but if you do, if you ever have to deal with Unicode, not just as a thing you're channeling through your system, but actually semantically, there's a huge amount of more detail to Unicode. There's lots of complexity here, which you might have to get into. So, just to review the facts of life, the 5 facts of life. 1, I/O is always bytes. Files and networks are always bytes. Fact of life number 2, you can't make everyone speak English. Fact of life number 3, you need both bytes and Unicode. You can't write a program that only deals with one or the other. Fact of life 4, you can't infer the encoding, you have to be told, so figure out where you're going to get that information from. And 5, be prepared one day for it to be wrong. And pro tip, the 3 pro tips are, write your code as a Unicode sandwich. It's all Unicode on the inside. If you find a byte string in there, find out where it came from, go all the way back to the source, and decode it when you get it. And then hold on to Unicode all the way until the end. 2, make sure you know what kind of strings you're dealing with, bytes or Unicode. And 3, test everything. And if you do that, then you'll be okay. And you'll have like the okay sign and the thumbs up and the smile with the sunglasses. These are a few more resources. bit.ly/Unipane is where all these slides are right now. You can go and look at it. Those links are very handy. Thank you very much. I want to give a shout out to all of the Unicode characters that helped me make the presentation. Any questions?
So I have 3 questions. 2 of them might be off topic or frivolous. So I'll tell you what they are first. My first question is about domain names that are Unicode and phishing. My second question is about languages that are not yet represented in writing or in Unicode. And my third question is about constructed languages like that science fiction fans make up.
Like Klingon? Like Klingon?
Yeah.
Yeah. So let's answer the Klingon question first, since it came up. There are spaces in Unicode which are just called private use area, which means that Unicode won't say what it means, but if you and a friend of yours agree on what that space means, then you can use it for whatever you want. And Klingon is in there. There's a group that is assigning private area code points to constructed languages, fictional languages, all those sorts of things, and that's where Klingon is in the Unicode standard. Things that don't have a writing system, I don't know.
Well, my basic question was, so you said 10% of the Unicode code points are used.
Yes.
Eventually, maybe those languages will survive and they'll have writing systems. Do you think they'll just end up using Roman characters or something like that, so they're not tromping on?
Lots of languages have very recently created alphabets for themselves. Cherokee is a famous example, but there's lots of others. And there are recently invented alphabets in the Unicode. I mean, a lot of these characters essentially are recently created. By the way, all these weird characters are because the Japanese have a big set of emoticons for use in texting, which is where a lot of these came from. What was the third one?
The third one was, so basically there was this thing going on for a while where different means were proposed to support domain names in Unicode. And it was decided that was a bad idea because of the possibility of phishing.
Right, like the snowman.org or whatever it is.
Yeah, because you can make domains that look like other domains, deceptive.
Right, and I think what's happening now is that the browsers will display some different coloring or something in the address bar if you have one of those domains, I think is what's going on. But I'm not entirely sure.
Okay, I wanted to ask what you think about usernames on like social sites. Do you think they should always be ASCII?
I have no opinion on that.
Okay, that exhausts my questions. Thank you.
Okay, sure.
Hi, thank you. Great talk. Where my head explodes is in your slides for 2.0, 2.x. You had capital H, lowercase I, space, then code points. What's happening with the HI in space? Those aren't code points. Those look like ASCII.
They are code points. ASCII is the first 96 code points in Unicode.
Aha.
Yeah. So the first. So I should have made this clearer. So ASCII is a subset of ISO-Latin 1, and ISO-Latin 1 is the first 256 code points in Unicode. So all of the stuff, Unicode is basically a superset of all of the character sets that have come before. Some of them are at the same values that they were before, like ASCII and ISO-Latin 1. Others had to be moved someplace else. So ISO-Latin 2 through 16, all those characters are in Unicode someplace. They're just not at the same values they were at before.
Leslie, do you know how you get on the committee that decides pile of poo?
I have no idea.
No? Okay.
I can't imagine that would be fun, but okay, maybe.
So Python 2 by default uses the system encoding for converting from Unicode to strings, right? So how does Python figures out the default system encoding? Is there any way to change it?
The default system encoding is ASCII because it's the only safe guess. Because everyone agrees on what those low 127 byte values mean. So that's why it's the default. It can be changed, but it's really difficult, and it's not a great idea. And the reason it's not a great idea is that however you change it, that is going to be outside of your program. It's an environmental setting. And if you change it, then your program will only work in that environment in which you've made that change. The better thing to do is to not have any implicit decoding.
I mean, it might be useful if I'm running a web server. I would like to actually make sure my server won't crash. I would like to set my default encoding to something which is quite safe, probably UTF-8.
Okay. Do you remember pro tips 1 through 3?
Yeah?
You should use those.
Okay.
Use explicit encodes and decodes and know what you've got and do the decoding so that you have byte strings outside and Unicode inside. And that's the way to make sure that your web server isn't going to have a problem.
No, I'm asking this question because I've seen like a program which actually works on my laptop and then some user complains that it's not working. So there's something there with the default encoding of the system. So I want to like how that works, and is there any way to change that?
That story is exactly the reason you shouldn't fiddle with it. Because however you would now have to ship that user 2 things, the program and the instructions for how to configure the environment so that the program will work. And it's much better if you can make it so that your program will just work.
I mean, I agree with that point, but it's still useful to able to reproduce the bug on a different machine.
Yes.
So
so get default encoding in sys module. There is a way to change it, but it can only be changed extremely early in the Python process.
Okay.
It cannot be, by the time your program is running, it's too late to change it. But you can go into site.py and change what value goes in there.
Can it be changed by setting an environment variable or something?
I don't know.
Okay.
No. Could be. Hi.
2 questions. You glossed very quickly over the byte order mark. If you open a file in text mode and there's a bomb in there, will it say, oh, I know how to deal with that? Or if not, is there a way to ask it to?
There is a way to, we've been using UTF-8 encoding here. There is a UTF-8 encoding with an extra little thing at the end. I forget what the name is. That means it's okay to have a bomb. Okay, the thing about the byte order mark is it shouldn't appear in UTF-8 streams at all, because it's really a way to distinguish between UTF-16 big endian and UTF-16 little endian, and it's nonsensical in UTF-8. But there's Notepad. So there's lots of data out there that is UTF-8 with a bomb, and some people say the bomb is a great marker to mean this is UTF-8 because it's 3 bytes that won't occur in, for instance, ISO-Latin 1. And there is I think it's UTF-8-SIG, which means decode as UTF-8 and don't complain when you see the bomb.
But what about storing in UTF-16 and having a bomb at the front? Will open handle that?
I believe so, yeah.
Okay. And my other question is, so for this sort of crazy character stuff, and then there's the other characters in Unicode that look identical to ASCII characters, like Greek capital alpha, looks exactly like a capital
A look identical.
How do you normalize that? And I imagine it's a matter of degrees. Turning umbrella into T is probably difficult, but turning capital alpha into A, you probably should do.
Why would you want to do that? Why throw away that information?
If you're writing a website and you want to look for swear words, the kids hide it in these characters and you want to find them.
Okay. The Klabutic problem, I know. Yeah. I don't know what to do about that. So on the last resources slide here. The Unicode data module in Python has a remarkable amount of information about the Unicode characters, if you need to deal with them semantically like that.
I run a feed reader, so I see a lot of different encodings.
Yes.
And so I found the easiest way to cure my pain is to go into sitecustomize.py, import sys.set default encoding, UTF-8. Is that a sin?
Yes.
It's worked for a while, but why?
Why did it work?
No, why is it a sin? I know why it works.
That goes back to the earlier gentleman's question. It's a sin because your program isn't correct without that tweak. Right? You've basically created an unusual Python environment in which your program works better, rather than writing a Python program that just works better.
You just need site customized py somewhere on your Python path, so you can put it inside of your program. It's not like you have to change the environment or have sudo access or wherever Python is installed. You can put it locally.
Yeah.
But it breaks if
Sure.
Yeah. And by the way, when you get to Python 3, that's not an option, right? You're tweaking the implicit encoding and decoding that doesn't even exist in Python 3 anymore. So,
thank you.
Yeah.
Very nice talk, Ned. I want to give another tip. There's a module called I/O in recent versions of Python 2.7, I think.
Yep.
And it provides the same interface for opening files with automatically encoding and
Yes.
decoding that Python 3 has.
Right.
So that's, I think, is useful.
Right. So his point is that new behavior of open, which has encodings and gives you either byte strings or Unicode, that is one of the things that's been backported from 3 into Python 2, but you have to use the I/O module in order to get it. Yeah. Any other questions? Alan.
Just one more point of pain. If you print a Unicode string and your terminal supports UTF-8 or something like that, Python will try to convert it, and it will succeed unless you run it through a pipe like less, and it'll fail surprisingly then.
Right. So what Alan's pointing out is that it's what I mentioned about standard in and standard out. Standard out has already been opened for you, so you cannot determine what its encoding is. And Python, if you are piping into a file, will give you UTF-8, but if you're going to the terminal, we'll use the locale setting of your shell, which if it isn't UTF-8 will be different. So you might have a program that works when you just run it and fails when you pipe it into a file or vice versa, which is counterintuitive, to say the least. Anyone else? That's it. Thank you.